So what we're starting here is kind of three things that build off each other. So we got a unit on velocity, and then that basically is how you describe motion. And then we're going to have a unit on acceleration, which is the rate at which the velocity changes. And then we're going to have it on a unit on forces, which force equals mass times acceleration. So it's like if you don't know what velocity is, you can't calculate acceleration. If you can't calculate acceleration, then you can't calculate forces. So that's kind of the trifecta of this whole thing. So today is what we call like a good news, bad news day. Okay, it doesn't happen very often. So the bad news is that I have to talk the whole time. The good news is you're not going to have any homework tonight. So that's kind of the trade-off, right? So all things considered, it's not bad. So when you look at velocity, it's the most intensive unit in terms of vocabulary in the words that we use. Most of the time you talk about physics, it's mostly a mathematical description. But with velocity, it's all about the terminology. And so one of the first things you have to get straight, and this is on the kind of lecture I sent out yesterday, is this idea of frame of reference. So frame of reference basically just talks about what you're seeing, okay? And so here's like the classic example. So right now, I can make the argument that Brooke's velocity is 0, okay? Mainly because within this frame of reference of this room, her position isn't changing. Now, when you talk about position, one of the things you have to establish is what we call the reference point, which is basically a point within the frame of reference that you're going to judge all the positions on. So, for example, Brooke could describe her position relative to the water jug. She could describe her position relative to the camera. She could describe her position relative to the door, okay? Doesn't make any difference. It's arbitrary. So the same thing is going to be true, like for example, one of the things we're going to do is we're going to talk about objects that are thrown up in the air. So if I make my hand the reference point, you would say that the object is going away from my hand, it's going up, and then it's coming back to my hand. Valid. But if you make the ceiling the reference point, then you would say, oh, it's going towards the ceiling, and then it's going away from the ceiling. It doesn't make any difference. If I drop this, and then we'll get into this a lot, if I drop this, I can describe this one of two ways. I can make the point of release the reference point, oh, it's going away from it, or I can make the ground the reference point and it's going towards it. If I make this the reference point and that's going to be described as 0, here's the other choice that you have to make. Oh, am I going to make those positions going down here positive numbers, or am I going to make them negative numbers? There are no right or wrong answers. It just depends upon how you set up the system, okay? So, but how you define your system is going to be, important in terms of how this whole thing lays out in terms of the bigger picture. So that's why, and that's why when we start to do problems, I'm going to ask you, hey, what's your reference point? Do you want to make the ground the reference point? Do you make the ceiling the reference point? So what we're going to do is we're going to work through like this big example, all right? And as we go through this, I've done this long enough that I kind of know the preconceived notions that you all want to bring into this. And I'm going to do my best to kind of, in this example, kind of smash those preconceived notions. Because if I don't, and studies have been done on this, so as a teacher, if you kind of have a preconceived notion about something that's wrong, and I in any way reinforce that, then it just becomes incredibly difficult to fix that later on. So that's why as we go through this, I want to make sure from the beginning that these wrong preconceived notions that you have, that I get rid of them right from the get-go. So what we're going to do is we're going to look at a simple example. So we're going to look at the great state of Kansas, okay? right? And we're looking at 3 different points. Wichita, Kansas City, and Winfield. Okay? Now, what we're going to assume initially is that everything is along this same line. Okay? So, initially, we're not going to be talking about something moving in a circle or anything like that. So imagine this is just one big, massive number line, okay? Wichita, Kansas City, Winfield. So we're going to start in Wichita, go to Kansas City, we're going to come back, end up in Winfield, and end up back in Wichita, okay? So that's going to be the trip. Wichita, Kansas City, Wichita, Wichita, Winfield, Winfield, back to Wichita. Okay, so that's going to be the big trip, okay? So we've got our frame of reference, which is the state of Kansas, right? And we could make anything the frame of reference. We could make the entire earth the frame of reference if we wanted to. We could make the universe the frame of reference. And that's why when you look at, hey, is Brooke at rest? Well, within the frame of reference of this classroom, she is, because her position isn't changing relative to whatever point that she picked. Now, but if you're on the outside looking in and you're looking at the spinning earth, right now Brooke is traveling at about 400 meters per second because she's on this spinning rock. So if you're outside the earth looking at Brooke, oh, there's Brooke. She's on this rock that's spinning. Well, then you could shift that even further and go, well, Brooke's on a rock that's orbiting the sun, and this rock is moving in space. Oh, okay, so now she's on a moving rock. Okay. Well, then if you get even bigger, our sun is part of the Milky Way galaxy, and we're on what's called a spiral arm galaxy, and our entire sun and everything else is moving around the center of what they think is a massive black hole at the center of the galaxy. So now we're moving around a black hole in the Milky Way galaxy. And then if you get even further, our Milky Way galaxy is moving through space, right? And the whole galaxy is moving, as all galaxies are. And eventually we're going to collide with another galaxy called the Andromeda Galaxy. Don't worry about it, it's a long way off, okay? It's going to be kind of cool to see, but it won't happen for like another 100 million years, so we'll screw everything up before we get to that point. So, but when you look at if you're moving or if you're at rest, it depends upon your reference point. So, we're going to start in Wichita and we're going to go to Kansas City, right? So here's the deal. And then we have Winfield. So Elise, what do you want the reference point to be? You want the reference point to be Wichita, Kansas City, Winfield, Garden City, Paris, Sydney, Australia. What do you want the reference point to be?
Kansas.
We got that. That's our frame of reference, is the entire state. But we're going to start in Wichita, we're going to go to Kansas City, and we're going to go to Winfield, back at Wichita. So we need to pick one of these 3 points to be the reference point.
Kansas City.
Okay. You can do that. But to make this simple, okay, because we're going to start in Wichita, and I'll show you that that will work, but let's make Wichita the reference point, mainly because that's where we're going to start. Where you start doesn't have to be the reference point, but it's going to make life simpler if we do. Okay? You must be partial to Kansas City. It's like, oh, I like Kansas City. Well, I do too, but we're going to make Wichita the reference. Now, Brooke. So we're going to make this 0. So do you want Kansas City to have a positive position or a negative position?
Positive.
Okay, so we're going to make Wichita the reference point. So that's the reference point. And we're going to work in kilometers because of the fact that we have such big numbers. So then we're going to make Kansas City's position be 300 kilometers. And we're going to make Winfield's be negative 100 kilometers. Now, this is what we could have done with Elise if you wanted to. If you had made Kansas City the reference point and made that 0, then this would be like negative 300 and this would be negative 400. Okay? we could have done it that way, but then we would have had a whole bunch of like negative numbers, and it still could have worked. We still would have got the exact same result, but then we just had to deal with a whole bunch of negative numbers. So that's why it just makes it a little bit simpler if you make that 0. Okay? We could make Kansas City, but it's just going to be awkward. It's like talking to a freshman. You can talk to them, but it's just awkward. Okay? You know? All right. So, one of the things that we'll talk about in this deal is what we call a vector quantity or a scalar quantity. Now, so I've got a short little video clip here. Oh, come on, play.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah!
No, I will not do that. I'm going to tell you that right now. Okay. So, and if you're not sure, and if you can't remember that definition, right up here, here's your definition of vector, and it came from that little skit right there. One of the kids made this in final design. So, if something is a vector quantity, okay, it has two things. It has magnitude and it has direction. Okay, now the magnitude is just a fancy way of saying it's a number. Okay, that's all it is. It's just a number. Scalar quantities are just a magnitude. Okay, it's just a number. So you can kind of visualize this with a banjo. Okay, so we're going to use a banjo in today's lesson. So basically, it's horribly out of tune, by the way. So if you look at something like we're going to go on this trip, okay, so we're going to go from Wichita to Kansas City. So basically, because we're talking about a direction, whichever direction the banjo points, so if it's something that we could represent with a direction, in other words, this banjo is going to point in a particular direction, that's a vector quantity. So we're going to talk about like displacement, okay? Displacement is where you're going to go, okay? Well, if I say, hey, Brooke, you know, where'd you walk in from? Well, I walked in from the parking lot. Okay. So if I know Brooke was out in the parking lot, then I know that she's going to walk in a particular direction to get in my class. And then that's also going to be, well, she's going to have a velocity. Oh, okay, that's going in a particular direction. So she could have an acceleration. Oh, she's accelerating in a particular direction. Oh, that required a force, which was in a particular direction. So, and she could have momentum. So the ones we're going to deal with most that are vector quantities, initially, are displacement and velocity. Okay? We'll eventually get into acceleration, force, and momentum later on. Okay? So basically, if it makes sense to visualize it with a banjo pointing in a particular direction, that's going to be a vector quantity. Now, in contrast to that, you can talk about scalar quantities. Scalar quantities are just a magnitude. So if I say, for example, I've got this spoon has a particular mass, okay? It has a mass of 5 grams. Well, that's just 5 grams. It isn't 5 grams in a particular direction, okay? Time, right? Time is 5 seconds, okay? It doesn't go necessarily in a direction, okay? Now, I know the argument is, well, you can't go back in time. That's true. And so that's why time is only going in one direction. So it's only going to be 5 seconds, whatever that is. Okay, speed, right? And you'll see the difference between speed and velocity in just a second. But speed is a scalar quantity. Now, when you look at your car and you're driving your car, right? And you're trying to figure out how fast you're going. You have a speedometer, right? You look at your speedometer. Your speedometer says, hey, I'm going 40 miles an hour. If I know you're driving 40 miles per hour, that's just a magnitude, okay? I don't know which direction you're going. I just know that you're driving 40 miles an hour. That's it. That's all I know. Now, if Brooks says, hey, I'm driving 40 miles per hour north to get to school, then that becomes a vector quantity. Because now I know not only how fast she's going, now I know which direction that she's going, okay? So your cars has a speedometer. It only tells you how fast you're going. It doesn't tell you the direction. Because if it did tell you the direction, then it would sound something like out of Jurassic Park. Because if it gave you direction as well, then that's what we call a velocimeter. Because it would tell you how fast you're going, and it would tell you the direction. Then it becomes a velocity indicator, okay? So that's kind of going to be the big thing. Speed is just a scalar quantity, it's just a number. But if you know how fast you're going and in which direction, then it becomes a vector quantity because then you know both. And the same thing is going to be true of distance and displacement. So if Elise says, hey, I walked 5 blocks to get to school, great, okay? If that's all she tells me, then that's just a scalar quantity. I just know that she walked 5 blocks. But if she says, hey, I walked 5 blocks east, oh, okay, then that becomes a vector quantity because not only do I know how far she walked, I know in which direction that she walked, okay? All right, so when in doubt, we're going to set up a chart, okay? Oh, that was a horrible line. So okay, so on the first trip, I'm going to draw this a little bit smaller down here. That's cool. Okay. All right, so here's the deal. So the first trip we're going to make, we're going to start at Wichita and go to Kansas City. So maybe like you want to go to the Cheesecake Factory, okay? Or see the Royals game or see the Chiefs play, something like that, okay? You're going to drive from Wichita to Kansas City. Now, you got to get used to this nomenclature. So when you see something with a knot on the end of it, that means that's the initial one or the original one, okay? So whether it's position initial P naught, velocity initial V naught, position or momentum initial, whatever it is. So whenever you start with something, we always put that knot on the bottom to indicate that's the initial value, okay? And then the other one is just that doesn't have the knot on it, that's going to be the final one, okay? Now, anytime you calculate the change in anything, whether it's change in position, whether it's change in velocity, change in acceleration, whatever it is, there's no exceptions to this. It's always something minus P naught, okay? Like position final minus position initial. If it was velocity, it would be velocity final minus velocity initial. So you don't have to think and go, oh, is it P naught minus P or is it P minus P naught? It's always something minus the original one, okay? Always. Temperature doesn't make any difference. It's always the same. So your displacement, and this is going to be important later on, is going to be P minus P naught, okay? So because of the fact that we're going from Wichita to Kansas City, okay, that's going to be our trip. So that means I'm going to come in, hold on, let me do this slide. So that means my initial position is 0, my final position is 300, okay? Let's say that took 3 hours. So, Brooke, what's my displacement? Positive 300 or negative 300?
Positive.
Yeah, because I'm just going to go 300 minus 0, right? Okay? So that's going to be 300. Because I took 300 minus 0, that took 3 hours. Now, our velocity is I want to take displacement and divide it by time, which in this case is going to be 300 kilometers divided by 3 hours, which is going to give me 100 kilometers per hour. Okay? It's cool. Life's great. Now, here's the deal. When you calculate velocity this way, and you take displacement and divide it by time, and we'll talk a lot more about this. I'm just going to lay the groundwork. You can use this and take displacement and divide it by time, but you can only do that if you're traveling at a constant velocity. If you're accelerating, meaning like you're speeding up or slowing down, you can't do that. So if I take this golf ball, right, and I move it like this at a constant speed, I can take displacement and divide it by time. Okay, not a problem. Now, if I throw that golf ball up in the air though, and that velocity is always changing, then I can't do that. And then I've got to calculate velocity another way. So, displacement divided by time. It's a wonderful idea, okay? It's just displacement divided by time. It's not a big deal. But, you can only do that if you have constant velocity, all right? So if you're speeding up or slowing down, once we get into the acceleration unit, you can't do that anymore. You can only do that when you have constant velocity, okay? All right. Now, there's a couple of ways that we can represent this. Let me go back up to that bigger one. So here's how some different ways that we could represent this. One option is that we could draw, because this is a vector quantity, we could draw a displacement vector pointing in this direction, okay? So this would be my displacement vector. So it's like the banjo. Okay, hey, the banjo is pointing towards Kansas City. So this tells me which direction that I went. So that's the direction part. And the length of that arrow is going to tell me the magnitude. Oh, that's how far I went, and that's the direction that I traveled. Okay, it's a vector quantity. I could also represent that with a velocity vector. And I could sit here and go, okay, here's my velocity vector. It's pointing in this direction. It tells me how fast I'm going. Okay. That length represents 100 kilometers per hour. And it tells me the direction that I'm going. Okay, so I've got those two things out of the way. Now, here's what you're beginning to formulate. Okay? Human beings are very, very good at recognizing patterns, okay? That's what allowed us to evolve, okay? We saw patterns. Oh, the wildebeest always showed up at this particular time. Oh, the river always flooded at this particular time. The moon always rose at this particular time, right? We're very good at seeing patterns, right? Now, here's the deal. You all are starting to begin to formulate a pattern right now, because that's what human beings do. And this is the first one that I have to squash. At this point, you're going, oh, I'm going away from the reference point, and I have positive velocity and positive displacement. So therefore, that must always be true. If I'm going away from the reference point, I have positive velocity and I have positive displacement. No. Okay, get that out of your minds right now. It is true in this circumstance, okay? If I have a positive, in this situation, I do have a positive velocity, and I do have a positive displacement, okay? And I am going away from the reference point, okay? And that's true. But that's not always going to be true, okay? So here's the first thing I want you to block out, okay? Don't sit there and go, oh, positive velocity means that that I'm going away from the reference point. It could be true, but it's not always going to be true, okay? So block that out of your minds right now. Okay, so at this point, we've gotten to Kansas City, okay? We're there, right? So at this point, you look and you get a Snapchat story or Instagram or I don't know, some random means of communication. You've heard that there's a big party back in Wichita because somebody's parents are out of town, okay? Timmy's parents are out of town. Timmy's always throws the best party, okay? This is pre-COVID, because I know you all would never gather or anything like that without your mask and everything like that. So, imagine this is pre-COVID. So, you go, man, we got to get back to Wichita. It's like, we can't miss this party. Come on. We got to go. All right. So, we're going to turn around. We're going to head back to Wichita. So, on the return trip, now we're going to go from Kansas City back to Wichita. So now my initial position, and here's the difference. Now my initial position is 300 kilometers, and my final position is going to be 0. Now, Elise, now what's my displacement? Beautiful. Why is it negative? Fantastic. Now, that's a very simple idea, but it's very profound, because I can guarantee you, you mark my words, here's what's going to happen. You're going to see these two numbers, and I'm going to say, what's the displacement? And you're going to go, oh, it's 300, right? That's what you're going to do. But you have to pay attention to the fact that this is final minus initial. Okay? It is always final minus initial. So, when you do this, this is why it's so important that you have that negative 300. Now, here's the difference between displacement and distance, okay? The distance between Wichita and Kansas City is 300. The distance between Kansas City and Wichita is still 300, because distance is a scalar quantity, okay? Because it's just 300. Oh, how far did you go? 300 kilometers. Okay, that's it. That's all you have to worry about. Because distance only has magnitude. It doesn't have a direction associated with it. But if something's a vector quantity, then it has magnitude and direction. So this is why displacement, and Lisa did a beautiful job. She said, oh, Ms. Burkamp, I'm not going to fall for your tricks. I'm going to take 0 minus 300, and I'm going to get negative 300. Now, in spite of it still being a huge party, okay, you're not going to speed because you don't want to get a speeding ticket on the way home. So it's still going to take 3 hours. So now my velocity is negative 100 kilometers per hour. Now, okay, now if you go back up here, now look what happens. Come on. So now, my displacement vector is pointing in the opposite direction. So we had the banjo. It was pointing towards Kansas City. We got to Kansas City, we're going to turn around, whoop, and now we're going to go back this way. So as soon as that banjo, whoop, changes direction, right? We went from positive to negative. As soon as that changed direction, right? That arrow started to point in the opposite direction. Now, the same thing is going to be true of our velocity vector. Now our velocity vector is going to be pointing in this direction. Okay? Now, here is the very, very first golden rule, and this is what's on that sheet. Okay? Anytime an object changes direction, the velocity changes sign. Okay? There is no exceptions to this rule whatsoever. None, zero, zip. It might be positive to negative, it might be negative to positive. But no matter what, if something changes direction, the velocity has to change sign. Okay? No exceptions. So if I take this ball and I throw it up in the air, okay, on the way up, it's going to have a certain velocity. Okay? It's going to be pointing in a certain direction. On the way down, it's going to change that direction. Okay? No exceptions whatsoever. So no matter how complex the motion is, if you see an object change direction, the velocity vector change sign. Negative to positive, positive to negative, doesn't make any difference. Okay? If I'm going to the moon, if I'm going to Mars, whatever that is, okay? If an object changes direction, the velocity vectors change sign. Now, here's what you're trying to formulate the next pattern. You're going, oh, Bergkamp, I see a pattern here. Okay? And the pattern is that you're trying to formulate is that if I go away from the reference point, I have positive velocity, and if I go towards the reference point, I have negative velocity. Okay? And that's true in this case. Okay? That is absolutely true in this case. But it's not an absolute truth. Okay? So, a lot of times that is true, but it isn't an absolute truth. Okay. So, here's the next thing. So let's say it's foggy, it's icy, whatever, okay? You're talking, you're staring at your phone while you drive, which is stupid, but let's say that you did that. And you completely miss Wichita, okay? You drive right past Wichita, and you end up in Winfield. And you're like, whoa, this is bad, okay? Because if you've ever been in Winfield on a Friday night, it's like, no, we got to get out of here. Okay, so you realize you're in Winfield and something bad has taken place. Like, how did we miss Wichita? We completely drove past it. So, on the next trip, we're going to go from Wichita to Winfield. So now, on the next trip, I'm going to start at 0, because now I'm looking at just Wichita to Winfield. Okay? So we could have 0, and then because of the fact that we're defining Winfield as being a negative value, that's going to be negative 100 kilometers. Okay? Now, here's the story. So, Brooke, what's my displacement from going from Wichita to Winfield? Is my displacement negative 100 or positive 100?
Negative?
You say that with absolutely no confidence. Brooke, displacement is position final minus position initial, right?
Correct.
So I'm going to take negative 100 minus 0. What do you get?
Negative 100.
Beautiful. Okay? There. See, this is the same answer. We're just a little bit more confident. Like, oh, God, stuck it. Okay? So that's going to be negative 100 kilometers. Now, let's say that that took 1 hour. Okay? So there's an hour of your life that you're never going to get back. Okay? It's like, wow. Yeah, that's just gone. Okay? So now, look what happens. So now, notice that my velocity vector is still pointing in the same direction, okay? This is why my velocity is still negative 100. Even though I went past the reference point, my velocity vector didn't change sign because of the fact that it's still going in the same direction, okay? So my velocity vector here is still pointing in this direction. It's still pointing down at negative 100, okay? So even though I went past the reference point, so this is why I said, okay, hey, you've got to get out of this idea that if you're going away from the reference point, it's positive velocity, and if you're going towards the reference point, it's negative. And that was true initially. So you can think of this in terms of like this banjo, okay? So if I'm going to walk along in this direction, so I'll make my coffee cup the reference point, okay? So that's the reference. So I'm going in this direction, the banjo's pointing in this direction, right? Okay? Going away. So then I'm going to stop, I'm going to go back. So now my banjo is going to point in the opposite direction. Now, once I go past the coffee cup, my banjo is still pointing in the same direction. Because even though I went past the coffee cup, I'm still going in the same direction. The banjo is still pointing in that same direction. So this is why, even though I went past the reference point, my velocity vector didn't change sign. There's something in my eye. Because I'm still going in the same direction, okay? So, we're down here, we're in Winfield. Position vector is still pointing in that same direction. Velocity vector is still pointing in that same direction. Now, at this point, here's the tricky part. Okay? Here's the tricky part. The tricky part is I can't get this thing to erase. Okay, there we go. So here's the grand finale. So at this point, we realize that we're in Winfield. It's like, this is bad. Okay, we got to get back to Wichita. We are so out of here, right? So I'm going to start in Winfield, negative 100. And then my final position is going to be 0. Okay, so we're out of here. So Elise, what's my displacement? Again, you say that with absolutely no confidence.
Positive 100.
Why is it positive 100? Your answer is absolutely perfect. Why is it positive 100?
Is it 0 minus negative 100?
Fantastic, okay? It's a beautiful answer. So my displacement is going to be position final minus position initial. So my final position is 0 minus a negative 100, right? So there's an hour. So here's the deal. Now we turned around, and now our velocity vector is pointing in this direction. So in this situation, and this is the whole point of going through this story, okay? This is the whole point. Is that when I change direction down here, my velocity vector changed sign, okay? That was the whole key to this. My velocity vector changed sign. But now I'm going towards the reference point with positive velocity. So that's why I said you've got to think this through and get out of your minds the idea that positive velocity means that you're going away from the reference point and negative velocity means that you're going towards the reference point. It can happen, okay? And that's what happened. But I can also go past the reference point and I can move away from the reference point with negative velocity. I can go towards the reference point with positive velocity. So when you hear positive velocity, there are certain things I want you to get out of your minds, okay? Number one, positive velocity doesn't mean that you're going forward, okay? Negative velocity doesn't mean that you're going backwards, okay? It has nothing to do with forwards and backwards, okay? Positive and negative are arbitrary based upon your number line. So, and here's what you want to look at, is that if we had stuck with Elise's system, where we made this the reference point 0, and we made this negative 300 and this negative 400, everything still would have been the same, okay? We still would have gotten the exact same displacements, we would have gotten the exact same velocities. Everything would still look the exact same. The only thing that would have been different is that it would have been a lot more complicated in terms of the negative signs, okay? So it doesn't make any difference. So that's why I said, hey, I throw the ball up in the air. Well, what's the reference point? I don't know, my hand. All right, fine. Do you want up to be positive or negative? Brooks says, hey, I'm a positive kind of person. I want up to be positive. Okay. So it would have positive velocity vectors on the way up. Then it's going to change direction, and then it's going to come back down. And then it would have negative velocities on the way down. Now, Elise says, no, Brookham, I went down to be negative. Or excuse me, I went down to be positive. Okay. So in Elise's system, there would be negative velocities on the way up. There would be positive velocity vectors on the way down. Doesn't make any difference. But here's what would, no matter which system that we pick, those velocity vectors are going to change sign once it starts back down. So it would be negative velocity vectors on the way up. It's going to be positive velocity vectors on the way down. Or positive on the way up, negative on the way down. Doesn't make any difference. They just have to switch signs. Okay, y'all been sitting, stand up, stretch for a little bit. I'm going to drink some coffee. Now, we'll stop that camera for a second. I can't wait till I can teach without a mask again. Okay, so here's the next big thing, and this is, continuation of those lecture notes that I gave. So imagine that I'm going to start to walk, and Brooke's going to have a stopwatch, okay? And Brooke's going to keep track of where I am as a function of time, right? Now, in this situation, I'm going to start at 0, 0. Okay, so I'm going to start at the reference point. Now, here's golden rule. There's some more like bronze rules. You don't have to start at the reference point, okay? But you're going to have some assignments later on where you're not going to start at the reference point, okay? In this situation, because we're just kind of getting our feet wet, we're going to start at the reference point. But you don't have to start at the reference point. So imagine this, that, my coffee cup is the reference point, right? So Brooke's going to when I say go, Brooke's going to start the stopwatch, right? And I'm going to keep track of where I am. So we're here, right? So Brooke's going to start it. I'm going to start moving, okay? After 3 seconds, I've traveled 6 meters, okay? So, traveled this distance, 3 meters. Okay, excuse me, 3 seconds, traveled 6 meters. So at this point, I've got two different points on this graph. I know my initial position, I know my final position. So if you were to just look at this in terms of a math class, and I said, hey, we're going to find the slope of this line. So I'm going to take 6 meters minus 0 meters divided by 3 seconds minus 0, and I would get 2 meters per second. Okay? Now, here's the deal. If you're in a math class, okay, you can just say, oh, the slope of this line is 2. Okay? 6 minus you know, 0 over 3 minus 0, and you can just say, oh, the slope is 2, okay? And in math classes, you can do that, okay? You can just say, oh, the slope is 2. But what's going to be vital as we go through more and more and more complex graphs is that the slope is going to represent a physical quantity. But you don't know what that physical quantity is unless you pay attention to what the units are. Okay, so that's the biggest thing that has to happen. So, when you look at this line, so here's one of the golden rules, that on a position time graph, the slope equals your velocity. Okay? Not the speed, right? Represents your velocity. So, here's the deal. So, if I've got these 2 points, I can find the slope of this line. Here we go. Now, and it doesn't make any difference which direction this thing is going. If it's sloping up, sloping down, doesn't make any difference. The slope's going to represent your velocity. So I have moved a particular distance, right? I was here, my banjo pointed in a certain direction, okay? I was going in this direction. There we go. Now at this point, I'm going to pause for dramatic flair, okay? So I was here, right? I walked the 6 meters, and then I'm going to stop. Okay, now I'm going to chit-chat a little bit. I'm old, I'm tired, you know? It's been a long day already. I've had enough coffee. I'm going to stop for a little bit, okay? So at this point, this line becomes horizontal. Now, is the slope of a horizontal line, go back to your math class days, is the slope of a horizontal line 0, or is the slope of a horizontal line undefined? Which one is it?
0.
Why? You're right, but why is it 0?
I don't know, I'm just remembering like $1.
Okay, so here's the deal. Here was 1.3 seconds, 6 meters. Now, over here, I'm at 4 seconds and 6 meters, right? Okay, so slope is always change in y minus change in x. True? That's what slope is. So if you look at this on this horizontal line, I would have change in y, which would be 6 meters, minus 6 meters divided by 1 second. Check my math, 6 minus 6 is 0. 0 divided by 1 is still 0. So, and at my age, you get nervous when people say this, like, oh, it's a flat line. It's like, oh, once you get past a certain age, the term, oh, it's a flat line, oh, it's a little close to home. So I have this horizontal line with no slope, right? So anytime you're at rest on a position time graph, that's shown by a horizontal line because you're at rest because your position isn't changing. Now, if you look at slope, okay, if you look at what slope represents, so when you have this line with this slope of 2 meters per second, okay, it's subtle, but it's important. What we're saying is that for every second that goes by, my position changes 2 meters. Okay, that's what that means. At the end of 1 second, I was at 2 meters. At the end of 2 seconds, I was at 4 meters. At the end of 3 seconds, I was at 6 meters. So when you look at velocity, it's called a rate function. And we're going to deal with a whole bunch of different rate functions. Okay, rate of change in position, rate of change in velocity, rate of change in momentum. Okay, whole bunch of different things. So basically, the steeper this line is, the faster I'm going. So 2 meters per second isn't all that fast, right? Now, let's say Elise is on a dead sprint and try and cut somebody off on the soccer field, okay? So if Elise is on a dead sprint, okay, she's running really, really fast. So in that case, in 1 second, instead of traveling 2 meters, she might travel 6 meters, okay? So Elise might move all of 6 meters in 1 second. So if that's what's happening, okay, if she's traveling that far, then in 1 second she's traveling a greater distance. So when you look at the slope of a position time graph, the steeper that line is, the faster that object is moving. Because in each interval of time, they're traveling a greater distance, okay? So if I decide, hey, I really don't want to, you know, I'm old. I don't want to move 6 meters in 3 seconds. Maybe I want to move 6 meters in 6 seconds. Well, if it takes me 6 seconds to get there, then this line becomes a lot more shallow because of the fact that I'm not moving as fast. Did I start that camera back up?
It's blinking.
Huh?
It's blinking.
I don't remember that started it back up. Yeah, I did. I get a little bit paranoid because I've done that before, like I didn't start it back up and I got to go back and record the lecture again, and that's not a good feeling. So, but I thought I did, just had to check. Okay. So now I'm at rest, right? So at this point, let me kind of get rid of some of this. Okay. So now I'm going to move really, really fast. Okay. Now, so here's the deal. So, Brooke, this line is steeper. But did I change direction? How do you know? You're right, I did not change direction. How do you know I didn't change direction?
Still going upward.
Yeah, okay, remember. This is a positive sloping line. Think back to your math class days, right? This is a positive sloping line. This has no slope, I'm at rest, right? So this is still a positive sloping line. So that's one way you can look at it. Like, well, it's still a positive slope. That means slope represents velocity. My velocity is still positive, I'm just going faster. So it didn't change direction. Now, here's the other way that you can look at it. Is that I was going away from the reference point, right? I stopped, paused for a second, and then I moved really, really fast away from the reference point. So, because of the fact that I'm still going away from the reference point, that means I'm still going in the same direction. Okay? Does that make sense? Okay. Now, and then I'm going to pause again, okay, for a second. Okay, so now I'm going to stop, I'm going to catch my breath, right? But now, I'm going to go back towards the reference point. So now I'm going to come back like this, right? So now I'm going to take this stroll across like this, and I'm going to go this direction. So if that's the case, now this line is going to come down here like this. So let's say that's 10 meters, and that took me all of 2 seconds, right? So here's I'm going to scale this down, right? So I'm here, okay, started at the reference point, moved a little bit, stopped, moved really, really quickly, stopped for a second, and then I'm going to go all the way back to the reference point. Okay? So I'm here, moved, stopped, moved, stopped. I had to do this crab thing, right? Now we're going to end up back here. So, in terms of the banjo, I was here, boom, stopped, nothing, boom, stopped, nothing. But now I got to take this banjo, I'm going to flip it all the way around, and now I'm going to go like this. So, as soon as that banjo flipped over, okay, so as soon as that banjo flipped over, what do you know about the sign of the velocity vector? Yes, beautiful. So I have positive sloping line here, I have positive sloping line here, then what's going to happen? Oh, right. Now I'm going to have a negative sloping line that's going to come down here like this. So, Now, this is going to be going like this. So now when I calculate that slope, okay, how do I want to do this? So now I'm going to have my final position. And again, this is why it's so important that you pay attention to what your final position is and your initial position is. So my final position is going to be 0. So now I'm going to have 0 minus 10 meters. And that's going to take me 2 seconds. Which is going to be negative 5 meters per second. So, look what happened. I changed direction. My velocity changed sign. I went from positive to negative, right? I went back towards the reference point. Now, here's the deal. At this point, okay, going in this direction. Now, I'm going to go past the coffee cup, okay? I'm going to go way over here, right? Go way over here. So when I do that, when I go way over here, when I go past that coffee cup, Brookway, and this line continues down here like this, when I went past the coffee cup, did my velocity vector change sign? Why didn't it change sign? What did when I went past, so here's my banjo, right? I'm going in this direction, okay? So, going like this, right? I'll go past the coffee cup. Did my banjo change direction?
No.
No. So if my banjo doesn't change direction, my velocity vector doesn't change direction. My velocity doesn't change sign. So because I'm still going in the same direction, okay? Still going in the same direction. Because I'm still going in the same direction, my velocity vector doesn't change sign. The other thing that's going to happen is that this is still going to be a negative sloping line. Okay, it's still going to be a negative sloping line. So now I'm going to redraw, I'm going to clean this up a little bit. Okay, so because right now this is horribly confusing. So I'm going to draw this a little bit bigger and go, there's like 10 seconds. There's my position. Time. Okay? So here's the deal. So if I look at my displacement, I'm going to end up here at -2, right? Now, so here's my reference point, that's 0. So I'm going to end up here at -2, right? So if you look at position final minus position initial, our final position is going to be -2 meters, because that's where we're going to stop, because I ended up over there. My initial position is 0, so on here, my displacement would be -2 meters, and then I would divide that by however much time it took. I'm still going to have a negative displacement. I'm still going to have negative velocity, because I'm still going in the same direction. The slope still has the same line, okay? It's not a big deal. So then I'm going to stop. So if you see, so I stop, and then I'm going to return back to the reference point. So this entire journey, if I were to act it out, I'm here, I'm going to move, I'll stop for a second, I'm going to move quickly, stop for a second, then I'm going to go all the way past the reference point, I'm going to stop for a second, then I'm going to end up back at my coffee cup, right? So any time, if you look on a position time graph, so let me draw this kind of all in one fell swoop. So any time, this is the position time graph. So any time a position time graph changes slope, changes the sign of the slope, okay? Not the slope changes, but the sign of the slope changes. That's when you're going to change the direction. So here I'm moving, stop, I keep moving in the same direction. The value of the slope changed, but I didn't change the direction because all I did was just speed up. Now, here I go from positive to negative slope, then I'm going to change the direction. Now, if you're a math nerd and you've studied like relative maximums and relative minimums, okay? So, anytime you have like, and we'll show this on curves as well. Anytime you have a relative maximum or a relative minimum, that means that you are going to change the direction because that means your velocity is going to change sign. Okay? Now, in this situation, I've got positive sloping lines or negative sloping lines, and they're straight, right? They're the same slope. So when you have some kind of straight sloping line on a position time graph, this is what we call constant velocity. Okay? So when it's a straight sloping line, it's called constant velocity. Now, but realistically, a lot of times things are speeding up or slowing down. It's like when your car starts at rest and you speed up, you don't instantaneously go to 15 miles an hour. It's like, oh, I'll press down on the gas pedal, whoo, and get to 15, just like that, right? So a lot of times we have to show it when things are speeding up or slowing down. So if you have, and we're going to look at, we call this like the football curve, okay? So one option on this football curve, okay, I'm going to look at all three of these. Okay, you can also, if you know Mick, if you ever seen like Mick Jagger, he was a member of the Rolling Stones, okay, and Mick Jagger was always known for these huge lips. Oh my God, I'm Mick Jagger and I've got these huge lips. So if you're a music fan, you could refer to this as like the Mick Jagger lip curve. If you're a football fan, oh, it's a football field. So here's what's going to be important. This is going to be on a position time graph, right? So on this position time graph, if we're going to look at three lines, A, B, and C. Now, B is obviously constant velocity, okay? Because that's a straight sloping line. In each interval of time, I'm traveling the same distance. Boom, straight sloping line. Now, Brooke, if you were to look at A versus C, one of those is showing an object speeding up, one of them is showing an object slowing down. So which one do you think is showing an object speeding up? Curve A or curve C?
C.
Why?
Because it curves up.
Because what?
Because it curves up.
Yeah. So the slope of this line is going to give you velocity, right? So if something's going faster, that line's going to speed up. Okay, it's going to curve up because that says in each interval of time, we're going to travel a greater and greater distance. If you have a curved line like this is mean that you're slowing down because you're approaching a flat line, which is going to show that the object is at rest. Okay? So if you're speeding up, the line's going to get steeper. If you have a straight sloping line, you're at a constant velocity. If you have a line like this, you're slowing down. So A is going to be slowing down. C is going to be speeding up. Okay? So, if you think about when you're driving, you only have three options that happen when you're driving. Okay? You're either speeding up, okay? You're slowing down, or you have your cruise control set and you're moving at 40 miles an hour. Okay, that's it. When you're driving, those are your only three options. You're speeding up, you're slowing down, or you're moving at a constant velocity. That's it. There is nothing else. Those are the only three things that you can be doing. Now, eventually we're going to get into the fact that you can like change direction with your steering wheel. So basically what's happening, if you think about how you drive in terms of vectors, okay? So the purpose of your gas pedal is to make your velocity vectors get bigger. The purpose of your brake is to make your velocity vectors get smaller. And the purpose of your steering wheel is to change the direction of your velocity vectors. So from a physics perspective, you have 3 vector changing mechanisms in your car. You can make the velocity vectors get bigger, you can make the velocity vectors get smaller, or you can change the direction of those velocity vectors. Okay? That's it. When you drive, those are your 3 options. Now you're going to think like, because in years past, I've told that to kids that they think, Burkamp, they'll come back the next day and go, every time I drive now, I think about this in terms of vectors. Like, oh, look, I'm accelerating. Oh, I'm turning. Oh, look, I'm making, So if that happens, I'm not responsible for it. I'm just pointing that out. Okay, so we got that. Now, I'm trying to figure out how I'm going to play this out of time. Now, the next thing we can do, and I'm just going to introduce this, we'll finish this up tomorrow, is what's called a velocity time graph. Now, what we're going to do there is we're going to keep track of how fast you're moving as a function of time. So imagine that I bought the NERD package on my car, and my speedometer shows meters per second, okay? And so Brooke's going to be riding in the car with me. Brooke's going to have a stopwatch. And Brooke's going to keep track of how fast I'm going as a function of time. Instead of how far I went, she's going to keep track of how fast I've gone. So we're going to start here at 0. And after 2 seconds, I'm going to be going, let's say, 6 meters per second. Okay? All right? I'm going to be traveling 6 meters per second. So if that's the case, I can find the slope of this line. I can take 6 minus 2, and that's going to get me 3 meters per second squared. Now, Brooke, what's measured in meters per second squared? So what does the slope of a velocity time graph give you? Acceleration. So the slope of a velocity time graph gives you acceleration. So the slope of a position time graph gives you velocity, but the slope of a velocity time graph gives you acceleration. Okay? All right. So I need to, you all sat here long enough. I need to go next door to check on some stuff because I'm going to get that I just completely spaced off. And I need to print out some stuff for you guys anyway. So we're going to stop, read through those notes, and then maybe print out some stuff so you guys don't have to print it out at home. So let's just call it a day, and I'll print out and we'll make it happen. Better read through those notes.